Well, hello and welcome. In this video, I'll be covering section 2.1, which is over increasing, decreasing, and piecewise functions, as well as some applications. My goal for you by the end of the video is to be able to graph functions and look for intervals on which the function is increasing or decreasing or constant, and estimate some relative maxima and minima. I would like you also to be able to, when given an application, find a function that models that application, and then also determine the domain, as well as some function values, and then be able to graph that function. And lastly, to be able to graph functions that are defined piecewise. So first, let's talk about increasing, decreasing, and constant. So if you have a given interval and it asks you to identify whether something is increasing or decreasing, if you notice that it's rising from left to right, you can then say it would be an increasing part of the graph. Whereas if you notice that it's dropping from left to right, then we can say it would be decreasing on that interval. Now, if you notice that it happens to stay perfectly horizontal from left to right, in other words, it stays the same height, then at that point we would say over that interval it must be constant. So to dive a little bit deeper into this, a little bit more mathematical explanation for what's going on. A function is increasing, as you can see from this picture. This would be an example if it's coming up from left to right, but it's basically saying if I know that a is less than b and I plug it into the function and I get what f of a is and compare it with f of b, if f of b comes back larger than f of a, then it must have been coming up the page or going up the grid from left to right. Conversely, the exact opposite is going to be true for decreasing. So notice with this one, a is still less than b, but now the y value when I plug a in, it comes back larger than the y value when I plug b in. So that means it must be falling down the page or it's decreasing along that interval. As for a visual of what constant would be, if I plug in, notice again, if a is less than b, if I essentially plug those numbers in and I get the exact same value for every single pair of numbers in between or along that interval, then at that point I say for that interval it must be constant. Now, an application of why I would care for increasing and decreasing or identifying it is essentially this concept that's called extrema, or relative maxima and minima. So in this scenario, what these collectively are called are extrema. So if a problem ever says to identify all extrema, that basically means to find all max and min points. In order for a relative maximum to be there, it's saying at specifically this y value or f of c, then basically what it's going to say is that number, f of c, needs to be bigger than every other y value along that same area. So basically if points to the left and to the right have smaller y values than the point that we're trying to say is potentially an extrema, then at that point, if they're all smaller, I then can say that must be a high point or a maximum. At the same point, if I want to talk about minimums, a minimum is essentially going to be if I have this y value, f of c, and I compare it to every other f of x that's close to it, so all of the other y values just to the left and to the right, if it happens to come back less than all of those, then at that point that must be a low point or a minimum. Now here's a visual to maybe simplify that concept or that definition a little bit more. As you can see with what they have labeled as relative minimums, when you go to the left or to the right, so if I go to the left or to the right of that point, notice all of the y values of each of those points come back larger than the actual y value at C1. So that then means that point here, and it's very similar to this point over here at C3, those would be what we consider relative minimums because all the points that are relatively close, it happens to be smaller than all of the other ones. A relative maximum, on the other hand, notice is now the highest, and if I were to compare with some of the other y values to the left and to the right, they all would come back smaller. So I would then be able to say, okay, that must be a relative maximum. And again, this keyword relative, why we use relative for this one, is it's not the high or the low point of the entire graph, it's just in a small portion. So like if I, for example, said just focus on this one box, that's now the highest point inside that box. And similar thing you can say over here or over here. those 2 points happen to be the lowest point inside of that smaller portion of the graph, hence why we use the phrase relative, and then whether it's a maximum or minimum depends on what the other points are doing. So let's maybe try an example of this. If I said to just identify all of the increasing, decreasing, or constant intervals from this given graph, if we maybe try and highlight some of these things, looks like it would be coming down the page from left to right along this interval, coming down the page along that interval there, and another one over here. So if I were to just list out all of the decreasing intervals, since that seems to be what it was doing first, it would be from as far left as possible, because there's an arrow pointed there, until I get to, and ultimately I just list out the x values at which the change happens. So that switch is happening along this line right here. That x value is at -8, so everything below -8, it would be coming down the page. The next interval looks like it starts here at -2, but then stops when I get to 0. So from -2 until 0, that would be decreasing as well. And then I've got another one here that looks like it starts at 2 and stops at 5. So I would just say from 2 to 5, that interval is also decreasing. Now if I kind of do a similar thing now with the when is it coming back up the page, looks like it's coming up the page here, here, and here. So 3 intervals there. So if I list out all of my increasing, looks like it starts increasing after I get past -8, but stops when I get to the -2. Again, I'm only listing the x values, so even though these look like ordered pairs, it's really just saying from this x to this x, I'm either coming up the page or down the page. In this case, I'm talking about the coming up the page intervals. The next one starts here at 0, and then stops when I get to 2. And then the last one starts at 5, and it looks like because of the arrow, it increases for forever from there, so it would go on to a positive infinity. Important to note with all of these intervals, notice I didn't use any brackets at all, because at the numbers themselves, so for example, if I were to maybe focus on this -2, 6 point, at that point itself, it's in between increasing and decreasing. So at that number -2, it's not really doing either at any given point. As far as the rest of this, it did ask for when is it constant. Well, the constant part, do you see any horizontal or flat lines for it? There are no places where that would happen, so there's no intervals in which I would consider this constant. Now, as far as the high points and low points, or the extrema, looks like the 2 high points I have, I'll highlight with orange there, would be my relative maximum points. So I'll just go ahead and write out my relative max would be the -2, 6, as well as the other point 2, 10. My relative min values are essentially going to be this -8, 4, it looks like, because it came down the page then switched to coming back up. Looks like 0, 0 is another one that's a low point, as well as 5, 0. So now I'll just list those out. -8, -4 is one of the relative minimums. 0, 0 was another one. And the last one was 5, 0. So now let's talk about some applications of how functions can represent some situations. So for this one, we've got 2 nurses that are driving away from a hospital at right angles to each other. And they gave us a specific speed, 35 miles per hour, as well as 40 miles per hour. And just to remind you, distance would equal the rate times the time. So in this case, it's giving me a rate. So I got like a R1 and a R2. And then it gives me t. It looks like it wants me to represent this function using t as its input. So I'm going to leave that variable there. So I need to express the distance between the 2 cars as a function of time. And then it does want me to find the domain of the function. So let's go ahead and get a little visual of what's going on here. As you can see, we've got this 90-degree angle that's formed right here. And they are traveling this direction out from there. They're going away from each other. So if I wanted to represent the distance d of t, that happens to be the hypotenuse of this triangle, hopefully we can remember that we have a squared plus b squared equaling c squared, with this one where a could maybe be Matthias's distance, b could be Chiara's distance, and c would be my hypotenuse. So if I set that up, it looks like my distance in terms of t is going to be equivalent to the square root, because I would want to cancel this power of 2 on the c, which would then be 40 squared, or 40t squared, plus, and then 35t squared. So if I were to now try and simplify this on the inside, it looks like I should be able to square both those values on the inside. So if I square the 40 squared, that should take me up to 1600 t squared. And if I square 35, that should take me up to 1225 t squared. Those are like terms, so I should be able to combine those two values. Still is the function d of t. And if I add those two numbers together, I end up getting 2825 t squared, which I then could maybe simplify that number on the inside and maybe just round it a little bit, which turns into about 53.15, and the square root of t squared should give me t. But in this context, as far as what do I know about t? Well, t is representing time, and it seems to me that time cannot be negative, because I can't go backwards in time. And what I'm really doing right here is the second part of this problem, which is identifying the domain. So I've got my function for the distance that their two cars are away from each other, but when it comes to the domain, I can't have time be negative, so I know that t must be greater than or equal to 0. So again, this is just an application of how we can utilize function notation to represent a specific situation. In this case, there was, because of context, this idea of restricting my domain. Because it actually had an application in the real world, time had to be positive, so I just knew time had to be greater than or equal to 0. Now moving on to another example of how some functions can be represented. The last one, notice, was just a single function. This was now where we're going to get into this concept of what's called piecewise functions. So a piecewise function is essentially a function where it has different output formulas depending upon what their domains are. So in other words, if I said to plug in, say, 5 to this expression, I'd have to look at all of the instructions, or the domains, I just like to call them the instructions, off to the right first to let me know, out of the 3 options that I have, which one I would plug into. So let's just try a few examples out and just kind of see how this is going to work. I'm going to go ahead and actually, because this is multiple parts, I'm just going to highlight different parts for this. The first domain, or the top equation, or the one that I just labeled as number 1, it's every time x is less than -2, I'm going to plug into that expression, the x plus 1. So if I look at the numbers that I have, which ones are less than 2, what looks like -5 is going to be, as well as -3. If I do a similar thing with this second one, it says every time the number is between -2 and +3, I'm going to actually just say that the value, or the y value, is just a plain 5. So if I look at the numbers here, I've got 0. That falls in that -2 to +3 window, so I know 0 is going to be one I'll plug into the second equation. And then 3, it does say or equal to 3 with this one, so it looks like 3 is going to be also just plug into that middle equation. And then on to the last one, if I have x being greater than 3, I plug into this x squared expression. It seems like 4 is going to fall in that window, and 10 for sure is going to fall in that window. So if it helps to kind of color code, if you have to do multiple parts, by all means go for it. With each of these, I'm just going to now plug in those values and use the function notation. So f of -5, I'm supposed to plug into the top equation. That would be -5 plus 1, which then equals -4. If I did the same or similar thing for f of -3, I plug in, again, because -3 is less than -2, I'd plug it into that top expression. It'd be -3 plus 1, which would give me an answer of -2. If I move on to the next two, f of 0, again, f of 0 falls between -2 and +3, so I plug into that. In that expression, there is no variable to replace, so it's just going to be 5, just like it's going to equal when 3 is there. Again, it had the or equal to in that inequality, so 3 was included, so therefore the y value I would get back is still 5. If I go into the last two, f of 4, 4 is greater than 3, so I'm going to plug into this bottom expression. It says I'm supposed to square it, so that would be 4 quantity squared, which I then can simplify and say is 16. And f of 10 is along that same interval as well, so I only plug into the bottom expression, 10 squared, which would give me 100. So each one of these now, you can treat these like for every input that I had. So like -5 for this first example, I got an output of -4, so that would be like a point -5 comma -4 that must lie on this function. Could do the same thing with all the other ones. It would be -3 comma -2 with the one underneath that. Over here I've got 0 comma 5 as well as 3 comma 5. And then the last one I could say would be 4 comma 16 as well as 10 comma 100. So if I needed to graph this particular type of function, I could potentially use those points to my advantage and try and actually connect the dots in a nice way that makes sense. So let's go ahead and talk about what does a graph of one of these piecewise type functions look like. So with this one, notice we've got two expressions again. I've got one expression for everything that is less than 3. And then I've got a second expression for everything that's greater than or equal to 3. So it seems to me I'm going to go ahead and just put kind of this imaginary line on my graph that's going to separate two different kinds of graphs here. So on the left side of 3, it's going to be graphing the top expression, whereas on the right side, so number 1 is going to be to the left of that line I just drew, and number 2, or the second expression, is going to be everything greater than or equal to 3, so everything to the right. So this first one, if we actually look at both of these expressions, they're both linear. So this first one, it looks like it has a y-intercept that's at 0 comma 3, just because that's in slope-intercept form, and we know our slope would be 1/3. So if I were to use that to my advantage, I could then plot the point at the y-intercept being 3, and then just go up 1 and right 3 to come up with my slope. Now, it doesn't say to include 3, so since that line actually fell on top of that line, that would make sure that I end that particular segment with an open circle. As I go further left, I would just do the rise of 1 and the run of 3, but this time I'm going to the left, so it's going to be down 1 and then left 3. And I'll just keep doing that until I run out of grid. And now I could just connect them with a nice straight line because this was a linear equation. If I do the same thing now with the second one, this one just has a y-intercept that's at the origin because there's no number being added or subtracted. And then from there, I have a slope that looks like would be -1. So what I could do to kind of help me out is I know I'm only starting this graph at 3, so this idea of having a y-intercept really does not help because the y-intercept is over in this 1 area. So if I wanted to, I could just go ahead and plug 3 into the expression itself. So if I plug 3 in, 3 when it goes in gives me -3, or g of 3, use the proper notation, would give me just the opposite, because again it would be plug into this expression, that would give me -3. So if I put that on my graph, I'd go over to 3 down to -3, but this one's actually a closed circle because it was allowed to equal 3. And then from here, now I can do the idea of a slope, which would just be down 1 to the right 1, until again I run out of grid or feel like I have enough points to be able to draw a straight line. So this is one possible example of a piecewise function. Notice that sometimes they end up with this gap in between. So notice one of them was an open circle, the other one was a closed circle. That's always going to be dependent upon do you see an or equal to or not in these two situations? So this one right here, because it didn't have or equal to, I know it ended with an open at x equals 3. Whereas this one, the second one, I knew it was going to be a closed circle or closed point at that x equals positive 3. And let's do one more example of graphing these types of functions, one that's a little bit more complex. So notice again our kind of instructions or domains for the two problems exist right here. So at x equaling -2, it's apparently not supposed to be defined with this first expression, so I know if I plot a point that uses that, it's going to be an open circle, whereas at the -2, that's going to be closed because it does have the or equal to. In this case, it was only equal to. And if I look at the two situations here, I've got this expression, which is a little bit ugly, that maybe I could try factoring. So x squared minus 4 over x plus 2. It is undefined at -2 because it would make the denominator equal 0. So that kind of makes sense why I had to say for x not equal to -2, I could use this expression. If I go ahead and try factoring, if I have x squared minus 4, that would be able to factor into 2 parentheses x plus 2 and x minus 2. And notice what that allows me to see is that the x plus 2 divided by an x plus 2 actually would completely cancel. So this one really is just like graphing a line of x minus 2. So if I go ahead and just think of this like, well, everywhere except at -2, I'm going to just draw that line x minus 2. That has a slope of 1 and a y-intercept at 0, -2. I can go to 0, -2 and do a slope of 1. Going to the right, there's no issue because all of these numbers are not equal to -2, so I know for sure it's going to exist this way. And then if I keep plotting points, now I get to where x was -2. I got to remember that's an open circle, and then everything else is still defined. So everywhere except at that -2, I knew I had that line. Now I get to do this second expression, or second part of this expression, which was, I'll say it's equal to 3 when specifically x is -2. Well, that's just a point, -2, 3, which would just be, that's the only closed circle that I have. So as you can see here, even though it looked a little bit more ugly, I still have a similar situation in that at -2 there was potentially a completely different, I guess, height for that point, or there was a jump, if you want to call it that way, to get up to the defined value, and then it came right back down and picked up where it left off. So again, it would go forever to the left because it doesn't have any sort of lower part of this domain. Now, introducing these ideas of piecewise functions, there's actually one specific type of function that we have that is probably one of the most applicable uses of piecewise functions, which is called the greatest integer function. So what the greatest integer function is, as far as how we represent it, it's kind of this double bracket looking thing around it. So if you ever see that symbol, that is representing what's called the greatest integer function. You can also, in some calculators, see it written as int of x to represent the greatest integer. But essentially what it does is it takes whatever the x value is, so in this case the number that's inside, I just go to the greatest integer that's either less than or equal to that number. So again, integers, remember, are all the positive and negative values that don't have any decimals or are not fractions. So with each one of these, as far as the example below, if I had -4 or -3.6 or -3.25, all of those, the last integer that is less than or potentially equal to it, they would all have a value that would turn out to be -4. So that means if I were to plot all of these would all, on the left side, these would be like my x values, and they would all give us the same y value of -4. So these would create a whole bunch of constant intervals or horizontal line segments if I were to actually look at what this graph looks like. If I did kind of a similar thing with this middle one, -1, -7/8, and -0.25, those all, if I think of what is the last integer before them or potentially equal to them, they would all essentially turn into this -1. And lastly, if we look at the last one here, 0 or 1/10 or 0.99, the last integer before or equal to all of those numbers is 0. So again, if it helps, I'll just take this last example. If I just said 0 is right here, 1 is right here, I know that 1/10 would be maybe right about here. The last integer to the left of it would be 0. If I went to 0.99, that would be super close to 1. But if I went all the way back to what's the last integer before, once again, it would just prove it's equal to 0. So maybe let's just try evaluating some of these greatest integer function symbols at specific numbers. So if we look at this first one, the greatest integer of 2.5, if I were to think again on a number line, where is 2.5, and then what integer is just to the left of it? Well, that would come back as a value 2. If I had a whole number or integer, the greatest integer that is either less than or equal to it, well, that should just stay that exact number. And if I did one like this last one, negative 5.1, the last integer prior to that number, if we plotted it on a number line, would actually come back negative 6. So it's always the negative numbers that are probably the trickiest. So one trick of the trade that you might use to your advantage is it's always one less, or it looks like you kind of round up if it's negative, and then just keep that negative sign on it. Anything that's positive, you either keep it the same or round down to whatever the last integer was. So hopefully this video has been helpful in just introducing the concept of functions and some of the things that we can do, such as increasing, decreasing, constant, finding extrema, or even just dealing with piecewise functions, specifically, for example, one like this that is called the greatest integer function. But again, I appreciate you guys taking the time to do this. If you have questions, by all means reach out to us. I guess until next time, we'll catch you later.